Today, what I'd like to do is discuss black holes and talk a little bit about how big a black hole is and show you some rather straightforward ways that we can think about the size of a black hole and calculate its dimensions. So what I'll do here is show you something here from my desktop. I'm going to share my screen here. So today the question before us is, how big is a black hole? Before we talk about how big a black hole is, what I would like to do is introduce a concept here for your consideration. What it is a description of what we call escape velocity. And as you can see here in this small diagram here, I have a planet. In this case, I'm showing the Earth, and a rocket, which is launching from the surface of the Earth. And as it launches, it's going to accelerate to a high rate of speed. The question is, how fast would the rocket have to go in order to leave the Earth's surface and never fall back down again? Now, I'm not talking about orbiting. I'm talking about actually leaving the Earth's gravitational field entirely and never falling back down again. In other words, if you launch straight up in the air, how fast would you have to go in order for that projectile or rocket ship to simply fly off into space and not return? Now, you can think about this. This is exactly what the Apollo astronauts did in the late 1960s. Apollo 8, for example, left the Earth's surface. First, it went into orbit, but then it accelerated a little bit later to a high rate of speed and essentially flew to the moon. It left the Earth's gravitational field altogether and reached the moon. And the Apollo astronauts had to reach what is known as escape velocity in order to do that. So how fast does a rocket need to be launched from the Earth's surface in order to escape Earth's gravity? Here's the equation. If you're familiar with algebraic equations, it's a fairly simple one. The velocity required to launch off of the surface of the Earth and not return is equal to the square root of the quantity 2 times g times m divided by r. Now, in this case, g is a factor here, 6.673 times 10 to the minus 11th Newton meters squared per kilogram squared. Now, don't let this bother you. The units here seem a little bit strange, but as long as you put the numbers in newtons and meters and kilograms into the equation, everything will factor out fine, and you can use this universal gravitational constant g as it's shown here. Now, in this case, the mass of the Earth is almost 6 times 10 to the 24th kilograms. Now, what this means is a 6 followed by 24 zeros in kilograms. So this is a stupendously high mass. If you think of a kilogram is a little over 2 pounds, 2.2 pounds, if you're more familiar with English units. But imagine the mass of the Earth as 5.974 times 10 to the 24th kilograms, or nearly 6 times 10 to the 24th kilograms. And the radius of the Earth, if you're standing on the Earth's surface, to the center of the Earth, that distance is 6.378 times 10 to the 6th meters. In other words, a little over 6 million meters below your feet is the center of the Earth. And that is the radius of the Earth, we call it. It's an average number. It varies a little bit depending on where you're at. But that is essentially 6 million meters, or 6,378 kilometers is the radius of the Earth. So if you plug those numbers in and respect the units that I talked about up here, and you punch that in on your calculator, you come up with a number here of 11,189 meters per second. This is the velocity that you would have to launch a rocket from the surface of the Earth to escape the Earth's gravity altogether. And this is essentially the speed that the Apollo astronauts achieved in order to go to the moon. It's a stupendously high rate of speed, 11,189 meters per second. That's a little over 11 kilometers per second, or almost 7 miles per second. Imagine traveling at that rate of speed. But that's what it takes to escape Earth's gravity. So this is what is known as escape velocity. Now we can talk about the escape velocity of other objects. So we just calculated the Earth, and you see here I've listed Earth at the top of the chart here. The mass of the Earth, as we talked about, and the radius of the Earth, as we talked about here, are shown. And the escape velocity is 11.18 kilometers per second, or almost 7 miles per second. And if you prefer, 25,016 miles per hour. That's the speed that you have to launch a rocket at to reach escape velocity. Now, if you run these calculations for other objects, like the sun, for example, the sun is considerably more massive than the Earth. As you can see here, it's 1.99 times 10 to the 30th power kilograms. In other words, 2 with 30 zeros behind it almost. The radius of the sun out to the diameter that we can see it visually is 695,990 kilometers. And if you punch that into your escape velocity equation down here that we described before, you get almost 618 kilometers per second, which is 1,382,000 miles per hour. That's the escape velocity of the sun, launching from the sun's surface. Jupiter is another one that we can compute. Now you can see Jupiter is quite a bit less massive than the sun. It's about 1,000 times less massive than the sun, but it's still considerably more massive than the Earth. It's like 300 to 400 times as massive as the Earth. And the size of Jupiter is quite a bit larger than the Earth. And the corresponding velocities here for escape velocity are 59.54 kilometers per second, 37 miles per second. Compare that to the 7 miles per second for Earth. You can see Jupiter is stupendously higher gravity, and this escape velocity is much higher as well. Mars, on the other hand, is a less massive planet than Earth, and it's a little smaller in size. It's about half the size. So the escape velocity numbers are considerably less. As you can see, it's less than half. So 3 miles per second is almost all you need to escape Mars. The moon is smaller still. You can see the mass of the moon is about only 1% as much as Earth. And the radius is smaller, and the escape velocity is consequently smaller as well, as you can see here. Now, interestingly, Deimos, which is one of the moons of Mars, you can see the mass of Deimos, although it's still a lot, you know, from the absolute point of view, from a person's point of view, it's a lot of mass, but it's a very, very small radius. It's only 6 kilometers in radius. And the escape velocity here is actually pretty small. If you look at it in terms of miles per hour, 14 miles per hour would be enough to reach escape velocity for Deimos. In other words, if you were a really fast runner, you could run fast enough and escape Deimos altogether just by running. So you fast runners, think about that. Anyway, these are calculations for objects within our solar system, the escape velocity for those objects. Now let's take a look at it from the aspect of, let's say we know the velocity that we're going to be leaving the surface of a planet or an object. Let's say the velocity that we're talking about, instead of 7 miles per second like it would be for Earth, or 37 miles per second like it would be for Jupiter, or even higher for the sun. Let's say that we know our velocity is going to be the speed of light, which is 300,000 kilometers per second, or 186,000 miles per second. Let's say that we shine a flashlight straight up and it's moving, the light ray is moving at a velocity of 186,000 miles per second. At some point, if you have a massive enough object down here, that light beam will cease to be traveling up. It'll change direction and be trapped. It'll fall back down to the surface of the object, which has a radius here. So the question is, how massive is this object and what is the radius of this object? We can use this escape velocity equation that we've been talking about to make that calculation. But this is our thought experiment that we're talking about for imagining what a black hole would be like. So a black hole, in the case of a black hole, basically the velocity of light is stopped and brought back down to the surface, and the velocity corresponding to that is 186,000 miles per second. So let's calculate that. Let's say we take the sun. How big would the sun have to be? We know the mass of the sun, but could we turn it into a black hole somehow? And so again, here's the sun. It's the most massive object that we have in our solar system. Its mass, as I said before, is nearly 2 with 30 zeros behind it, kilograms. Its radius is almost 700,000 kilometers. The escape velocity is 618 kilometers per second. Now, let's say we took the sun and crunched it down. Let's say you had a big hand that you could grab the sun and just squeeze it down. Let's say you could squeeze it down to where it's 10% as big as it currently is. Same mass, but just we compressed it. Now you can see the escape velocity increased quite a bit. Now this should make sense if you're starting from the surface of a smaller dimensionally smaller object that has the same mass. It's going to have to travel further to escape, so it's going to have a higher speed leaving from its surface in order to do that. And you can see that's true using this escape velocity equation. The velocity would increase to 1,953 kilometers per second. Again, if we take it, crunch it down another 90%, so to where it's only just a little over 7,000 kilometers in radius. Now you can see the escape velocity has increased again. And again, we take it down another factor of 10. We've increased it to almost 20,000 kilometers per second. Again, we can take it down another factor of 10. That increases it to almost 62,000. If we take it down another factor of 10, we've reached 195,000 kilometers per second is what the escape velocity would be from an object as massive as the sun that is only 7 kilometers in radius. Now, if we cut it in half, now you can see we're approaching the speed of light. The speed of light is actually, as we said, it's almost 300,000 kilometers per second. But if we could crunch it down to something slightly less than 3 kilometers in radius, we would indeed have an escape velocity equal to the velocity of light. And were that to happen, we would have a black hole. It would be a solar mass black hole. It would have the mass of our sun. It would have the dimensions of something that it has a radius of only 3 kilometers. In other words, its diameter would only be 6 kilometers, slightly less than 6 kilometers. And its escape velocity would be the velocity of light, which is, by the way, 670, almost 671 million miles per hour. Now, we can rearrange our equation here, our escape velocity equation, by solving it algebraically for the radius. Instead of solving for escape velocity, let's solve for the radius necessary to achieve an escape velocity here equal to the speed of light, which we're going to call c. This is called the Schwarzschild radius. That's the size of a black hole. So whatever the mass of your object is, we can plug that in here. G is a constant that we talked about earlier, and the velocity of light is also a constant. It's 299,790 kilometers per second, and that gives us the radius of the object. It's called the Schwarzschild radius. Now, could the Earth be a black hole? Well, if we follow the same process where we take the mass of an object, the mass of the Earth, crunch it down, yes, we could reach a black hole for the Earth as well, but instead of being a radius of 3 kilometers, the Earth being so much less massive, we'd have to crunch it down to be the size of a penny. And if you did that, yes, you would have a black hole. Now, this is rather absurd. It could theoretically be done, but how are we going to take something as big as the Earth, crunch it down to the size of a penny? I don't know. But were you to be able to do that, you would have a black hole. But it's using the same method of calculation as we saw with the sun. The Schwarzschild radius for the Earth would be a little bit less than 9 millimeters. So here's an object that has been observed. We can observe this from the surface of the Earth using small telescopes, but we don't see much. It's called M87. Here's an image of it from the Hubble Space Telescope. M87 is a galaxy, and there's a black hole at the center of this galaxy. And based on a number of observations that have been made over the years, scientists have been able to calculate the theoretical mass of this black hole as being 6.5 billion times the mass of the sun. So in other words, if you had 6.5 billion suns and you brought them together at that point right there, you would have a black hole of the same size and mass as what we see here in M87. So 6.5 billion times the mass of the sun. Now, here is another image of the black hole at the center of M87. This particular image was taken by the Event Horizon Telescope, which is a worldwide array of radio telescopes that were electronically linked together and used to provide a very high resolution image of this black hole directly. Here we saw an image of the black hole from a single telescope, the Hubble Space Telescope, and here we see what it looks like in radio waves over a huge array of linked radio telescopes. Now you see something that kind of looks like a donut. And actually, yes, it is a donut when you think about it. The black hole is in the center of the donut, and we don't see anything there. And here is what we call the event horizon. And essentially that is a point at which if something goes inside of this event horizon dotted line that you see right here, that will be the situation where anything that enters that region will not be able to escape. So this is essentially the size of your black hole that we've been talking about. This is known as the event horizon. And if we were able to calculate the diameter of this right here to this event horizon, that would be how big this black hole is. And in fact, we can do that here. We can take the mass of this black hole, and here's your event horizon. And here is what we have termed our Schwarzschild radius. And if we do that using a mass of 6.5 billion times the sun, we get a radius here. This Schwarzschild radius is 127 astronomical units. Now, 1 astronomical unit is the distance between the Earth to the sun. So the radius of the Earth's orbit is 1 astronomical unit. And here we're talking about this radius here being 127 times the radius of the Earth's orbit, or 127 astronomical units. So this is a very, very large black hole when we think about it. Very, very large. Our solar system would fall into this and not even be visible. It's so small in comparison. Now, this outer portion here, this is theorized to be matter, gases, highly energetic plasma, and so forth, swirling around, orbiting around this black hole. Eventually, that material will get sucked inside of the event horizon and be sucked into the black hole, never to return again. But this is essentially what I wanted to talk about here today. The size of black hole is an interesting concept. Black holes can be differing sizes depending on their mass, but this is what we're talking about when we talk about event horizon, mass of a black hole, escape velocity, and the speed of light, and how those things all interrelate with each other. Thank you.